Hello everyone, Dr. Zia Tahir here. This video tutorial is about 2D truss analysis in ANSYS Workbench, and that is a description of the problem. A balcony truss shown in the figure. So that is a balcony truss shown in the figure. So all members are made from Douglas fir wood with a modulus of elasticity 1.9 into 10 to raise per 6 psi, Poisson's ratio of 0.3, and a cross-sectional area of 8-inch squared. Assume rectangular section, breadth at 2 inch and depth at 4 inch. So what's required here? Determine deflection of each joint, axial force and stress for each member, and reaction at each support under loading shown in the figure. So this is example 3.2 from chapter 3, Trusses, Finite Element Analysis Theory and Application with ANSYS, by Saeed Moaveni, 4th edition. So that is example 3.2, so the same one. The problem is that, but I have changed its description a little bit. That is a chapter 3 of Truss from this Finite Element Analysis Theory and Application with ANSYS, 4th edition. So steps for analysis of balcony truss in ANSYS Workbench. The first one to need to start project. Then in engineering data, add material. Then in geometry, select analysis type and then use design modular geometry to sketch that model. And then in the model, go to geometry and material assignment and then meshing, then applying boundary conditions. So in the boundary conditions, applying supports and then loads. Then in the solution required is a deformation, then axial force, then stresses, then reaction forces, and to solve, and then result fractional deformation, axial force, normal stress, and force reaction. So I am going to use all these steps to analyze this truss. And these are the highlights of this video. So the first step is to start project static structural in ANSYS Workbench. So this is ANSYS Workbench, and here you have analysis systems, and here is the static structural. So that's static structural. That is a static structural. So I'm going to save it somewhere in my computer. So I saved that project as balcony truss in my computer. Next step is in engineering data, add material, and it is a linear elastic with isotropic elasticity and defining value of E and nu. So the material is Douglas fir wood, modulus of elasticity 1.90 into 10 to raise per 6 psi, and a Poisson's ratio of 0.3. So here, engineering data, double click on that, and then here a new material, wood. And there's a question mark on wood, and in the linear elastic isotropic elasticity, just drag it here, and units of Young's modulus, that is psi, and its value is 1.9 e raised per 6, and Poisson's ratio is 0.3. So that material is added. So I'm going to save that material. So this material is saved, like these two and wood, and I'm going to uncheck that default material structural steel. And once you've done it, then you can close that material. So now that material has been added using engineering data. Next step in geometry, need to define analysis type and basic geometry option line bodies and analysis type 3D. So here in the geometry, these are the properties. So select line bodies and then analysis type need to use as 3D. Although this member, like this problem is 2D problem, but when you're going to do a 2D, so ANSYS Workbench do some weird stuff. It's not actually take that solution type as Truss, so you need to keep it as 3D. Next is need to start design modeler, and for that one here you have two options. Sorry, in the geometry, right click on that, and you can select either a space claim geometry or new design modeler geometry. So I'm going for new design modeler geometry, and it will take some time to open. So that is design modeler geometry, and in that one need to model that truss. So for that need to go to sketch first and then concept, line from sketches, and then generate. So here, so these are three for each member. Horizontal member, they are 3 feet long. Vertical member are 3 feet long. So in design modeler, first you need to set units to foot, and then XY plane in the sketching, setting, grid, snap on and grid on, and then 1 foot, and then measure is 1. So now need to draw it. Okay, so I will use that line. So that is the first 3-inch line, then that other horizontal line, that is horizontal line, then that vertical line. So, and then the diagonals. So that one is sketched. So now go to modeling. Here in XY plane, you have that sketch. So click on sketch, then concept, lines from sketches. Okay, apply. So they turn to blue. Then you will have lines here. So, and then generate that. And now you have that line body there. So next is need to generate cross section, and cross section in this example is and breadth as 2 inch and depth as 4. So now for that one, in the concept, cross section, rectangular, and here change units to inches, and its breadth is 2, and its depth or height is 4. So now that one, you can see that is the cross section, and then generate that cross section. So now you have that cross section generated. Next, need to go line body, select line body, and then assign cross section rectangular to that. So here click on line body. So cross section is being highlighted. So just click and select. So that one. So I have renamed that rectangular. Now in the line body, it is rectangular, select it, and then generate that. So now that part is being generated. So that one is being generated. So I can, in the setting, turn off the grid, and then I can see that part is generated. So once model generated, save it, and then close that one. Next step is a model. So for that one, double click on model, so that a new window is opened, and in the geometry, in the model tree, and then in a geometry, material assign, and then the model type is link or truss. So for that one, there's a question mark on geometry, line body. So material is wood for this, and then model type is beam. It's assuming it as beam, but it's not beam. So need to change that one to link or truss. Okay, so now that one, so that is a line body. So here, and then you can display its cross section. So that is a cross section displayed on that. Next step in the model, mesh, and in the sizing, select edge to mesh, and then number of divisions for that. So I'll go click on mesh, and then I'll try to generate that mesh. So once it's generated, so you can see that it is a random mesh. But for pin joint structure or trusses, we like the theory which we use. So there is only one element between the nodes. So for that purpose, need to add sizing. So sizing, click on that, and then select all edges. So for that one, here you have edges and then selection mode box. So click on that and then geometry. So all 6 edges are selected and you can see that these are the elements. So it says that element size and there is a default value. Instead of that, I'm going number of divisions and I'm going for 1. So that in between nodes, there is only one division and you can see that and then now generate mesh. So in this way, you can have that like between two nodes, only one element. So here in the display, in the preference, you can uncheck that. Okay, so the nodes numbers are not there, or you can simply here in the preference show node numbers and element numbers. Okay, so you can see that one. So once you have in the preference, so then in the display you can show node or there is an option for that one. So now the meshing for this one is done. So the next step need to go static structural and then environment, support, displacement, all nodes z equal to 0. So why is that? Because it is a 2D problem, but in abacus mechanical it is at 3D, so we need to restrict rotation any motion out of the plane, so along z axis. So for that one, go to structural speed. In the environment you have like sports and then displacement. So what I want displacement along z-axis for all nodes as 0, and for that one select vertex and then using here apply, and only I want to z component as 0. So now in that one, so it is not able to now, there is no motion out of the plane or along z-axis. Next step in the environment, go to sport, select either simply sport or displacement. So in the question, that is the first node and that is the third node. And for that first node, so both sports are simply supported, and on simply supported, there are two reactions. So it's mean that horizontal and vertical displacements are 0. So for that one, okay, so again in the static structural, so sport and then simple sport. So it says the geometry. So I am going to select that node applied, and this is simple sport. And remember that on simple sport, like displacement along x and displacement along y is 0. So I am going to say it as upper. Then similarly, here I can select displacement. Okay, and now for this one, apply. And in this case, I need to keep that x and y constant. So displacement, and that is, let's say, lower support. So now simply supported and displacement, they are the same because we are dealing it as a 2D problem, and here in the displace like in 2D, to keep it 2D, I have already restricted that Z. So for simple support, here X and Y are 0, and then the lower I have kept that X and Y as 0. So now this is, we have applied boundary conditions to that. Next step, in the environment, loads and force as components. Scoping method is geometry and vertex. Two loads are being applied, 500 pound each. Okay, so now in the design modeler, so you can check the units. So the units are inch, pound, meter, or you can keep it as foot pound. So now I want to apply one 500 downwards load here, 500 pound, and then another here. So for that one, environment, and you have force. Okay, so this force, it says that geometry selection. So on that node, apply and then define by. So here is components. So minus 500 pounds in the downward direction. So that is one force. So let's say force 1 is being, or load 1 is being applied again, or you can simply click on structural insert, and then here you have force. So I am going to name it as force 2. So that force is applied on this node. So just select that node, applied, and then here defined by components and minus 500. Okay, so that second load is also applied. So now in the structural, what we have, so we applied A and B boundary condition, simply supported, then, sorry, and then D and E, these are the loads. So now to check if the model is okay, just hit solve button and it will give you an error. So just ignore that error, and then you can see there is a green tick on the solution. So it's mean that model so far is okay. So next step is in the solution. So what is required? In the solution, deflection is required, axial force is required, stress is required, and reaction is required. So for that one, I'm just to check that what is deflection or deformation. I'm going to apply first total and then deformation directional and in X and Y axis. So for that one, here in click on the solution and you have that deformation. So total deformation and then directional deformation. So that is a directional deformation. So I need that directional deformation along x-axis. So that is along x-axis, and then another directional deformation. So I am going to name that as y, and for that orientation is y-axis. So that is total for total deformation and deformation along x and y axis. They are being uh, selected in the solution. So next step is to get axial force, and for that one in the solution need to go to beam results and then need to select axial force. So for that one, here in the solution, right click on that and insert, then you have here beam results and axial force, or otherwise you'll have that axial force here. Okay, and for that axial force, okay, that is axial force. Next step is stress, and axial stresses are required, so normal stress need to select. And for that one, here you have stress and stresses are not activated. So for that one, click on solution and it say beam section results. Click here, yes. Okay, and now you can see you have that strains and you have stresses, and click on normal stress, and then that normal stress you'll have get that normal stress in the solution. Next step to get reaction forces, and for that one, go to probe, then select force reaction, and then apply here that which boundary condition is required. And for that one, in the solution, here probe, and then in the probe, you have force reaction. So force reaction, and it says that boundary condition. So I am going to use that upper. So force reaction at upper support. And similarly again, probe, force reaction, and then select that lower, and I'm going to rename that as lower support. So now here you have that upper support, and then you have lower support. So now all that required in the solution, so they are being used here. So next step is solved because we have added all that parameters, required parameter in the solution. So it's very simple. So click on solution and then solve. It will take some time. It gives you warning. So, but just ignore that warning. And now you can see that you'll have all that solution there. So after solving the results, the first is directional deformation. So for that one, you'll have here. So that is the total deformation. Okay. So that is so undeformed and then deformed, and that is the total deformation. So it is in inches. So same question in the book is solved using ANSYS mechanical APDL, and that is the total maximum value is 0.3197, and you can see here. So so for that one, so the maximum value is at somewhere node, and it is 1.96 into 10 to the raise power minus 2. So you'll have that same here. And then here you have the deflection. So to get that at each node, for that one, go to probe, and then at each node, because on these nodes it is 0, and that is a very low value, and on these node it is somewhere 1.17 minus 3.52, and those values are closer to the values here. So next one is y. For that one again on these ones. So these are that are the deformation. So they are very much similar to that y values. Next step is to find axial forces. So for that one, here you have axial forces. Okay, so I am going to, okay, so for axial forces, so again probe, and for each one, so you can get that axial forces, or otherwise right click on that and export text file. So I am going to save that as axial force. Okay, and now it is being opened. So these are axial forces, and they are very much similar, exactly the same, like as minus 1500, 14.2, 500 minus 500 minus 707. So these values are the same. Next step is to get normal stresses. So for that one, here you have normal stress. I'm going to delete that previous one. So for the normal stress, the contour is very much similar to what we have previous. So I can, so these are the values of stresses, and on the same page you can have those, like these are the normal stresses. So the maximum one is 176.78 and a minimum 187.5. So here you can see these are the same values. Okay, so similarly, you can export those as a text file. So next step is to get force reaction. And for that one, force reaction in the upper. So that is force reaction in the upper one. It is like in X direction, it is minus 1500. In Y, it is 1000. And similarly, for the lower one, it is only in X direction, which is 1500. So this is how you can get those reactions. So that is step-by-step procedure to solve or to analyze that truss in 2D in ANSYS Workbench. So these are the steps. So I hope you like this video. Thank you very much for watching. So you can leave comments for feedback.